In this video I'm going to talk about implicit differentiation. But first I want to give some meaning to the term implicit. So if I have a function y equals, say, cosine of x cubed, this defines y explicitly in terms of x. Okay, so this is exactly how y relates to x. To get the y value, I simply plug something in for the x here, and I find out what it is. Okay, more generally, if you have y on one side and some function entirely in terms of x on the other side, then that defines y explicitly in terms of x. Okay, sometimes y is defined implicitly in terms of x by a relation. Okay, here we have x squared plus y squared is equal to 36. This relation here, since it's not written as y equals f of x, this defines y implicitly in terms of x. So if we have a relation that defines y implicitly in terms of x, and we want to find out dy dx, or how y changes as x changes, we have to use a different technique than in the case where we have y defined explicitly in terms of x. I'm going to focus on how to differentiate or to find dy dx when we have y defined implicitly in terms of x. I'm going to do a couple of warm-up examples before getting to it. Okay, let's take a look at d dx of the cube of cosine of x. Okay, so d dx of this is saying to find the derivative of this with respect to x. So we use the chain rule, and we bring the 3 down, we keep the inside, subtract 1 from the power, and multiply by the derivative of the inside. So that's equal to 3 times the cosine of x squared times the derivative of cosine of x, which is negative sine of x. So that simplifies to negative 3 cosine squared of x times the sine of x. All right, I'm going to do another example. Okay, to find d dx of the tangent of x cubed, we're going to do the same thing. So that's 3 times the tangent of x raised to the second power times the derivative of tangent of x, which is secant squared of x. Okay, just to hammer in the point, I'm going to do one more. Okay, to find the derivative of 1 plus x squared quantity cubed, we bring down the 3, keep the inside, subtract 1 from the power, times the derivative of the inside. So that's going to be 3 times 1 plus x squared squared times 2x. Okay, now I'm going to get into the implicit differentiation. So in each of these cases, I knew exactly what the function was in terms of x that was being raised to the third power, and I differentiated appropriately or accordingly. Now I'm going to say, suppose y of x is a differentiable function of x. I don't know what it is explicitly, but I do know that it's a differentiable function of x. I want to find d dx of y of x cubed. I'm going to do this exactly the same way that I did up here. So I brought down the 3, kept the inside, subtracted 1 from the power, multiplied by the derivative of the inside. So we have 3 times y of x squared times the derivative of y of x. The big difference between this example here and these 3 examples here is that in each one of those cases, we could find the derivative of the inside. When y is defined implicitly in terms of x, we do not get to find out what the derivative of that inside is. So we just leave it as y prime. Okay, so usually when you see these examples, you're not going to see it as a y of x. You're going to see it like this. You'll see d dx of y cubed is what you're supposed to find, and you implied in the problem is that y is really y of x, that it's a differentiable function of x. So if I want to do d dx of y cubed, I should think d dx of y of x cubed. So I'm going to use the chain rule. So it's 3, keep the inside, subtract 1 from the power, multiply by the derivative of the inside. Okay, so if y is a differentiable function of x, then d dx of y cubed is 3y squared times y prime. Okay, let's find d dx of y to the fifth. Again, I'm saying, suppose y really is a differentiable function of x. Then, instead of having y to the fifth, we imagine it's really y of x raised to the fifth. So then we bring down the 5, keep the inside, subtract 1 from the power, multiply by the derivative of the inside. And that's how we leave it. Okay, here I'm going to give you one to try on your own. Suppose y is a differentiable function of x. Find d dx of the square root of y. Press pause while you work on it. d dx of the square root of y is d dx of y to the 1/2. So that's 1/2 times y raised to the negative 1/2 times y prime, which is the same thing as y prime divided by 2 times the square root of y. Okay, so that is how implicit differentiation works. Okay, here's another one for you to try. In all of the problems in this video, because I'm not going to keep repeating it over and over again, in all the problems in this video, I'm going to assume that y is a differentiable function of x. Okay, so press pause while you find d dx of sine of y. Okay, this is really d dx of sine of y of x. So it's the derivative of the outside, the derivative of sine is cosine, evaluated at the inside, so instead of putting y of x, I'm just going to put y, times the derivative of the inside. Okay, so this is y prime cosine of y. All right, here's a tricky one. Why don't you press pause and give this one a go? Okay, hopefully you realize that this is actually a product, which means we're required to use the product rule. So it's the derivative of the first function times the second function, plus the derivative of the second function times the first function. Okay, in this case, we're differentiating something that is explicitly defined as a function of x. So in that case, we get to use ordinary differentiation. So the derivative of x squared with respect to x is simply 2x. So we have 2x times cosine of y. Now plus, now the inside is not explicitly defined. Now the inside is implicitly defined, y as a function of x. So to differentiate cosine of y of x with respect to x, the derivative of the outside is negative sine of x, negative sine, evaluated at the inside, times the derivative of the inside, and then here we have times x squared. So we get 2x cosine of y minus x squared, I'll bring out front, sine of y, I'll just leave it there, and then times y prime. Okay, the y prime only applies to the second term. All right, now you have everything you need to do the types of problems you're going to be asked to do. So let me give you an example of one of those. All right, here we have x squared plus y squared is 36. So this relation here defines y implicitly in terms of x. I want to find the slope of the graph at the point 0, 6. To find the slope of the graph of this, I need dy dx, and then I'm going to evaluate it at the point 0, 6. One way I could do it is to solve this equation for y, but then the derivative I'm going to be required to do is actually a lot more complicated than just simply using implicit differentiation. So I'm going to use implicit differentiation to find dy dx. Okay, so dy dx is, you'll remember, also y prime. The first thing that we're going to do is differentiate each side of the equation with respect to x. Okay, so the derivative of this sum with respect to x is we differentiate the first piece, and then we add the derivative of the second piece. So d dx of x squared, that's just 2x, plus the derivative with respect to x of y squared. We bring down the 2, we keep the y, subtract 1 from the power, multiply by the derivative of the inside, y prime, equals the derivative with respect to x of 36. That's a constant, so its derivative is just 0. So let's clean up this side. We have 2x plus, that's the power of 1, not a prime, so plus 2y times y prime equals 0. So the first step is to differentiate both sides with respect to x. The next step is going to be to isolate y prime. To do that, we'll bring 2x to the other side, and then we'll divide both sides by 2y. So we have y prime, or the slope function, is equal to negative x divided by y. So we want to find the slope of the graph at the point 0, 6. That means x is 0 and y is 6. So we have the slope, right? That's what I wanted. Yeah, find the slope. So the slope of the tangent line is negative the x-coordinate divided by the y-coordinate, which is negative 0 over 6, or 0. Okay, so that says the slope of the graph of this relation here at the point 0, 6 is 0. So that means we have a horizontal tangent line. And that makes perfect sense because the graph of this is a circle of radius 6. Okay, so we have the center is at the origin, the radius of the circle is 6, the point 0, 6 is this point right here. So we see we definitely have a horizontal tangent line there. So we better get 0 as our answer.